Let's take a look now at section 4.4, Properties of Logarithms. In a previous section, we defined a logarithm as the inverse of an exponential function. Now, logarithms themselves have certain properties on their own, independent of being the inverse of exponential functions. So here, let's go ahead and talk about some of the properties of logarithms that turn out to be rather useful. So this will be stated as a theorem. All right, let's begin with three numbers. Let b, x, and y be positive real numbers. Just like in previous sections, we're going to want b not to equal to 1, not because that's impossible, but because that doesn't give you a logarithmic or exponential function. It just makes everything constant. So we want to let b, x, and y be positive real numbers, and we want to make sure that b is not equal to 1. Okay? If that's the case, then the following three things are true. The first one is that if you take the logarithm of base b, and again, it doesn't matter what b is as long as it's positive and not equal to 1, log base b of x times y, that's the same as the logarithm base b of x plus the logarithm base b of y. Your book calls this the product property. The second property that's true is if you have the log base b, instead of having these multiplied in the argument, if instead they're divided, then that's going to equal to the log base b of x minus the log base b of y. And your book calls this the quotient property. And finally, number 3 says, if you have the log base b of x, and now let's say you take the log base b of x and multiply it by some number y, then that's the same as taking log base b, and instead of multiplying the whole logarithm by y, you can just raise the argument to the power of y. Just like that. So now let's go ahead and prove this theorem, or at least a part of it. Oh, my apologies. This one's called the power property. So now we can go ahead and prove one of these. Let's see here. Proof. I'm going to start with number 1. Let's begin with this side. Here, I'm going to do something with each of these two things. So let me take these two things and call them something simpler. I'll take log base b of x and I'll call it m. Okay, so log base b of x, we're going to call that m. And let me take log base b of y and let me call that n. Okay, just like that. Now, because of the way that these are defined, because of the way logarithms are defined, that's the same as saying, well, if log base b of x is equal to m, that means if I take b and I raise it to the power m, that'll give me x. All right, that's the definition of a logarithm. And same thing over here. Log base b of y is equal to n. That means if I take the base b and raise it to the n, I get y. All right. So now I notice that what I want to do is I want to multiply these two things together. Okay. So then that means if I want x times y, that's the same as, well, that's x times, and that's y, just like that. But now these are just bases with a power. And going back to chapter 1, when we look at basic properties of arithmetic and of algebra, We note that if you multiply two things that have the same base, you can do that by adding the powers. So here, that's the same as saying b to the power m plus n. I can add these two together in my new power. All right? So now I have another way of representing x times y. X times y can be represented as either of these two. All right, this is the one I'm going to be interested in here in a moment. All right, now, remember, I don't care about xy by itself. What I'm trying to do is I'm trying to prove something about log base b of xy. Okay, well, let's see. Log base b of x times y. Well, look, if x times y is the same as that, and that is the same as this, that means all of these are equal to each other. If x times y is equal to b to the power m plus n, then if I take the logarithm of x times y, that's the same as if I took the logarithm, with that base b, of b to the m plus n. If that is equal to that, then the log of this is equal to the log of that. But, look, log base b of b to a power. This is an exponential with a base of e. This is a logarithm with a base of e. And since logarithms and exponentials are inverse functions as long as they have the same base, here, this will go away, and I'm simply left with m plus n. So this implies that the log base b of xy is equal to m plus n. But remember, m and n were these things that we defined up here. So that's going to be log base b of xy is equal to, well, my m began as log of base b of x, plus my n began its life as log base b of y. Okay? Looks just like that. But that's what we wanted. Look, that's the first part of our theorem. Log base b of x times y is equal to log base b of x plus log base b of y. That is the product property. The other two properties can be proven in very much the same way. Number 2 can be proven almost exactly the same way as this one is proven, except that instead of having x times y, we're going to want x divided by y. So here, we're going to start off with these same two things. I'm going to take my m, I'm going to take my n, and here all of this will remain the same. Now, if I want x divided by y, well, then that's going to be the same as b to the power m divided by b to the power n. All right? If I multiply x and y, that was multiplying these two. So now dividing x over y will be dividing these two. But again, if you have two things with the same base and you're dividing them, the way you do that is you subtract their powers, the power of the numerator minus the power of the denominator. So, if what I want to do now is I want to take the log base b of x over y, well, that's the same as taking the log base b of this thing. After all, x over y is equal to b to the m minus n. So if I take the log of this, that's the same as taking the log of that. Oop, that should be my mistake. That should be log base b of b to the m minus n. I left off my b over here. But now, log base b of b to a power, these drop away, just like they did in the previous part of the proof, and I'm left with m minus n. So this will give me that the log base b of x over y is equal to m minus n, but m is the log base b of x, and n is the log base b of y. So here, this gives us the log base b of x over y is equal to my m minus my n. But that is the second property. Here, look, log base b of x over y is equal to log base b of x minus log base b of y. And our third one is left up to you. This is going to be one of your homework problems. It'll ask you to prove the third one. There's a little bit of, there's a little bit of hesitation for people to start proving things on their own. Here, this isn't on an exam, so there's no need to worry. The worst that can happen is you make a mistake, and we learn from our mistakes. If we try to do this one, one thing I will suggest is look at the results of number 1. If you look at the results of number 1, you'll realize that, hey, look, if I have, If I have x times y, I can do something with that. Well, what if these were the same? What if instead of x times y, what if this was x times x? I could think of that as x to the second power. Well, then that would be an x, but then that would be an x too. Well, what does that mean? Well, what if I had another one? What if I had x to the third power? What would that mean? So think about that as you prove it. It'll be one of your homework problems that you'll see when you get started on your homework. Okay, so now let's take a look at some examples of using these properties. Let's go and slide this down and leave it there for a while because we're going to be using these properties here. And let's take a look at some examples. Now, the reason we're going to want to use these properties in coming sections is going to be because logarithms can be a little bit complicated to work with. But if we can take something that's complicated one way and rewrite it another way, maybe this other way is going to be a lot easier to handle. Or maybe the other way around. Maybe this one's complicated for that particular problem, but rewriting it this way will be easier to handle. The main use of these properties is to give us some flexibility, to give us the ability to write expressions either with a big argument or with small arguments. You might have a big argument, but there's only one logarithm, or you might have little arguments, but you have several logarithms. And depending on the problem, it may be better to have one or the other. So for right now, we're only going to practice using the properties. We're not actually going to use it to solve anything. We're not going to use it to do anything other than to see how the properties work. In a coming section, we'll see how this is used in application. We'll see how this actually is used for other stuff. But for now, we're going to take a look at an example. And the first example tells us to condense. Condense. Well, what does that mean? When you condense something, that means we're going to take it from something that has several small pieces and we're going to put it together as one large piece. This can be done with just about anything as long as the logarithms that we have all have the same base. Notice that for all of these properties, you have a common base here. You don't have a base A and a base B. All the bases are exactly the same. So as long as we have all the same bases, these properties can be used to rewrite expressions into smaller, more condensed forms. So our first example, let's start off simply. We're going to do several of these examples all in a row. Let's say we have the log base 3 of x plus 1 plus the log base 3 of, let's say, 2x. Okay. Well, here I have two different logarithms, but they both have the same base, and they're being added. This first property tells us if we have two logarithms that are of the same base and they're being added, we could write them together as a single logarithm. Notice the base stays the same, but now instead of having two separate arguments, you multiply those arguments together to give you your new argument. So here, this would be condensed as log base 3, and we would multiply these two things together. For right now, let me just write them next to each other, and then let me multiply them after that. Like that. So they would be multiplied together under a single argument. And so now if I multiply those together, I would get 2x times x is 2x squared. And 2x times 1 is, well, it's 2x. And there we go. We know we're done condensing because we're down to a single logarithm. Whenever you condense, you know you're done when you end up with a single logarithm like this. There are some exceptions, of course, but for all of the problems that we see in this section and in this chapter, that's how you know you're done. In more advanced classes or in more advanced topics, there are other complications that you may have to worry about, but for now, it's just we want a single expression with a single logarithm. All right, let's see that again. Let's say I have the natural log. Now remember, the natural log is the log of base e, but again, it doesn't matter what the base is as long as all the bases are the same. So if I take the natural log of 3x minus 5, and I subtract from that the natural log of x plus 1, this second property tells me that I can put those together as a single logarithm. Now I got to make sure it's the same base, so I still have to use the natural logarithm. And now the argument of the first logarithm is the numerator, and the argument of the second logarithm is the denominator. And my parentheses look strange. It really should be over the whole thing like this. All right? It's a single argument. Here, that doesn't reduce. We can't actually simplify that out very nicely, so we'll just leave that as our answer. We can say log base 5 of x plus, let's just say x. And let's say I want to multiply log base 5 of x times a single thing. Let's say I'm going to multiply it times the number 3. This third property tells me if I'm multiplying a logarithm by a number, then I can treat that number as the power in the argument. So here, instead of writing this as log base 5 of x, I'm going to still write it as log base 5, but instead of x, I'm going to treat this as a power on top of x. Just like that. Now, of course, our properties don't have to be used separate from one another. It's possible to write an expression that has more than one of these properties happening simultaneously. So let's take a look at something a little bit bigger. Let's say I want to condense 3 times the natural log of x minus 1 plus the natural log of, let's say, x minus the natural log of x plus 5, like that. Well, now we have a few properties. Notice I have a logarithm that's being multiplied by a number. And, well, that's that property. But I also have sums and differences, which be these properties here. So now the question is, which one or which ones do I want to do? And in which order? Well, the order of operations has never gone away. Hey, I have multiplication here, addition and subtraction. Multiplication should go first. So I'm going to use this property here to tell me, hey, I have a power here, or rather I have a factor here, and I'm going to turn it into a power up there. So I can write this as, and I'm going to do this in a few stages, I can write this as the natural log of x minus 1 to the power 3. Normally we would actually multiply that out, but for now let's just go ahead and write it out this way. Now that that's done, I can just go on down the line, because the only properties now left involve addition and subtraction. And the order of operations tell us that when we have just addition and subtraction, we just go left to right. So here, these two are being added. Well, if I'm adding two logarithms, I can multiply their arguments. So this would be the natural log of x times x minus 1 to the third power. All I've done is I've multiplied that x times that x minus 1 to the third power. It's multiplication, so it doesn't matter what order they're in. If I put the x on the end or on the front, it would be the same. I haven't used this one yet, so I'm just going to write it down. But now, if I'm subtracting, well, these do have the same base. They're both natural logarithms. That means I can now write those two logarithms as a single logarithm with these two arguments divided into each other. So, in the end, this will give me the natural log of, I'm going to take the argument of the first logarithm and treat that as my numerator, x times x minus 1 to the third power, divided by, and here that's going to be x plus 5 in my denominator. And you could, of course, now multiply this out, x minus 1 to the third times x, and then divide by x plus 5. But here, we're going to stop there. If you can get this far, I'm perfectly well satisfied that you understand what you're doing. All right? So now, let's take a look at another example. Let's say you have the log base 2 of x plus 3 minus double the log base 2 of, let's say, 3x. And then over here, let's go ahead and add, let's say, log base 2 of x minus 1. All right, so we're going to go ahead and condense this. At this point, you should pause the video and give this one a try. Once you've gotten to a point where you think you have the right answer, once you think you've condensed it down correctly, go ahead and unpause the video and we'll go through it together. All right, so let's go through this. First of all, there's some multiplication, and multiplication will happen before addition or subtraction. So this is going to be treated as the power of this argument. So let me do just that part first. This is log base 2 of x plus 3 minus, I'm going to square this whole thing. Now remember, when you square, you don't just square the variable, you're squaring everything. So here I'm going to write this as log base 2. If I square the number 3, that's the number 9. If I square x, well, I get x squared. Like that. All right. Now the next thing I want to do is, well, I have addition and subtraction. I just go down the line. So here these are being subtracted. So I can combine these with one argument, with this in the numerator and 9x squared in the denominator. So let's write that as log base 2, x plus 3 is my numerator, over 9x squared is my denominator. I haven't used that yet, so let me go ahead and write that, plus log base 2 of x minus 1. Okay. So now here, these are being added together. And since they're being added together, I can multiply these arguments. So this will give me log base 2 of, here I'm going to write them as x plus 3 over 9x squared times x minus 1. Now that might look a little weird, but remember, x minus 1 is the same as x minus 1 over 1. Anything is the same as itself over 1. So if you go ahead and multiply these together, you're just going along the top. So here we can write this as log base 2 of, now once again, up here you could multiply this out, or we could just leave it. Here I'm going to go ahead and just leave it. X plus 3 times x minus 1 over, well, 1 times 9x squared. Well, that one is just 9x squared. And if you really, really want, you could, of course, multiply it. Here I can write this as log base 2 of x times x is x squared. That's negative x plus 3x. Well, that'll give me 2x. And 3 times negative 1, well, that'll be negative 3 over 9x squared. There's a few other ways you might even rewrite that, but that'll work. Either of these is acceptable. You have condensed down until you have just a single logarithm, log base 2 of a single thing. Or if you wanted to write it this way, it's still log base 2 of a single thing. Now this is something that's important enough in use and application that we want to know it backwards and forwards. And here I mean that literally. So the next set of examples are going to have us do the same kind of procedure but in reverse. So here our examples are no longer going to be to condense but to expand. Expanding is the exact opposite. When you condense, you start off with several pieces that have small, simple arguments and put them together to get one expression with one big argument. Expanding would go the other way around. You start off with one logarithm with a complicated argument and then go backwards until you end up with a collection of logarithms that have smaller, simpler expressions, smaller, simpler arguments. So let's go ahead and take some examples of that. Okay, so our example, let's go ahead and expand the expression log base 5 of, and let's start off small. Let's just say 6ab. All right. Well, now that expression is made up of a single logarithm with a single argument. But notice in that argument, you have the product of things. Things are being multiplied. This is 6 times a times b. So what we can do is, instead of writing it as a single logarithm with two things multiplied together, we can separate it as a sum of logarithms, where each of these factors is an argument of a separate logarithmic expression. So here, we can write this as, now this is 6a times b, so you could write this as log base 5 of 6a plus the log base 5 of b. These two things are being multiplied together, 6a times b, so that's the log base 5 of 6a plus the log base 5 of b. But notice, these two are also being multiplied together. So you could split that up a little bit more. You could say that's the log base 5 of the first factor plus the log base 5 of the second factor. And then log base 5 of b was already there. And there we go. You might ask, well, how do I know when I'm done? How did I know I wasn't done up here? How did I know there was more to do? These are the only ways you can split apart your logarithms. If you have the product of two things inside the argument, you can split. If you have the quotient of two things inside the logarithm, you can split. Or if you have a power inside the logarithm, then you can pull that power out as a constant multiple. If you have a product, a quotient, or a power inside the logarithm, then that's something you can further simplify. But if it's not a product, a quotient, or a power, well, then there's nothing you could do. And that's how you know you're done. Here, I saw products, so I know I could simplify. I knew I could expand. Well, now here I saw another product, which means I knew I wasn't done. I could expand some more. Let's see that again. Let's say I'm going to take the common log. Remember, that's log base 10, although that doesn't really matter. It's just another logarithm. Now, let's say I have log of x to the power 2 over yz. Now, here we have a few things going on. Notice that I have a quotient. Things are being divided. I have a power. X has a power on it. And I have multiplication. Here, these are being multiplied just like they are here. Well, notice that the most overpowering operation here is division. What I mean by that is this, you're only squaring that one little part. Here, this, you're only multiplying those little things. But here, all of this is being divided by all of this. So division is the overarching operation. It covers the entire argument. So here, that's where I'm going to start. I can write this as the log, and that's the common log, of the top minus the common log of the bottom. When I have a quotient, I can take the top, treat that as an argument, minus, take the bottom, treat that as an argument. And that's what I have here. But now, this has a power on it. Okay, so now I can write this as log of x, and whenever there's a power in the argument, that can be brought out as a constant multiple. I can say that's log of x times 2. Now, incidentally, I keep saying constant multiple. This doesn't have to be a constant. In later courses, you'll see where this could be a variable or even another function. But for now, we're looking at just constants. Right here, this is also something I can split up. In fact, just like above, I have the product. I have the product. And if I have the product of two things, I can split that as the log of the first factor plus the log of the second factor. Now notice, this is minus. So in fact, let me write that in its own separate step. So here, that's 2 log of x minus. Now I'm about to split this up. So this is going to become log of y plus log of z. Right? Now this minus is this minus. So let me ignore that for just a second. Let's just see what happened to this part. Log of y times z is log of y plus log of z. Okay, cool. That's one of our properties. These are being multiplied. I can separate it as a sum. So notice that this became all of this. Okay, cool. Why'd you do the brackets there? Well, notice this minus applies to this. So this minus will apply to all of this. But whenever you have a minus that's applying to several pieces, well, that'll distribute. So here we could write this as 2 common log of x, and now we distribute our negative. That's minus the common log of y minus the common log of z. Notice that negative distributed out. Our next example, let's go ahead and look at, let's do a natural log. I like natural log because it's one less letter to write. I don't have to write log, just ln. I'm not even kidding. That's why I prefer natural logarithm in examples. It's one less letter to write. So I have the natural logarithm of, let's do 2x over the square root of, let's say y plus z. Like that. Okay. So now, same as before, we're going to go ahead and rewrite this. There's one big fraction here. Yeah, I've got a square root and a plus and a times, but that only applies up here. That only applies down here. Overall, the entire thing is being divided, one thing into another. That's the biggest operation going on. It affects the entire argument. So that's the one that I want to start with. So let me write this as the natural log of the top minus the natural log of the bottom. Just like that. You say, whoa, where did that 1/2 come from? Wasn't that square root? Well, remember, a square root and a 1/2 power mean the same thing. In fact, all roots can be thought of as a fractional exponent. Here, recall, the square root of a number is the same as that number to the 1/2 power. The cube root of a number is the same as that number to the 1/3 power. The fourth root of a number is the same as x to the 1/4 power. Fifth root is the same as x to the 1/5 power, and so forth and so on. So here we can treat this square root as a 1/2 power. Now you say, well, why'd you do that for? Well, because now, by treating it as a power instead of a square root, it makes it obvious that I'm supposed to do something with it. Because anytime I have a power in an argument, something happens to it. If I left it as a square root, it might not be obvious I was supposed to do something. But if I treat it as a 1/2 power, well, now it seems obvious. I need to do something with that 1/2. It's a power. So let's continue on here. The natural log of 2x. Okay, well, that's just like the very first one. That's 2 times x. So I can write that as the natural log of 2 plus the natural log of x. All right. Product separates as a sum. No big deal there. And now let me just rewrite that the way it is. Okay. Now right here, I have a power. And you say, well, yeah, but you also have a sum here. Well, yeah, but the power is affecting everything. Oh, okay, so that's the biggest thing in the argument. It affects everything. Here, plus is only between these two. So let's handle this part first. So we can write this as the natural log of 2 plus the natural log of x minus, now remember, whenever there's a power, it can be brought out, and you can say the logarithm times that power. So here's a 1/2, so I can say 1/2 times the logarithm. And we're done. Well, now you look at this and say, well, no, we can't be done. You got to separate that, don't you? Well, we'd love to, but we don't have a property that lets us do that. Notice we have a property that lets us handle if we have a product in the argument. We can handle a quotient in the argument. We can handle a power in the argument. But nowhere do we have any properties that tell us what to do if we have a sum in the argument. Now you say, well, look, no, I have a property that has a plus. Look, it's right here. Yeah, but that's a plus between two logarithms. Here, I need a plus inside of a logarithm. And I don't have anything like that. So because I don't have any properties that cover that situation, that means there's nothing I can do to expand that. So that's as far as I can go. Natural log of 2 plus natural log of x minus 1/2 natural log of y plus z. And that's as big as I can make that. Let's take a look at one more. All right, let's take a look at expanding the natural log of, let's say, 5y times x plus 1 to the power 2 over the cube root of 2 minus 7x. Just like that. All right, so at this point, go ahead and pause the video and give this a try. Expand this expression until it can't be expanded anymore. And once you've reached the nice stopping point, go ahead and restart the video and we'll go through it together. All right, so let's go through this. First of all, we notice that there's a big quotient here, there's a big fraction. All right, so that means that can separate as the natural log of the top, 5y times x plus 1 squared, minus the natural log of the bottom, 2 minus 7x raised to the power cube root is the same as a 1/3 power. So this is natural log of 2 minus 7x to the 1/3 power, just like that. So now let's separate each of these. Hey, look, I have a couple of factors. These are being multiplied together. So let me write this as the natural log of 5y plus the natural log of x plus 1 quantity squared. Let me leave this alone for now. I'm just going to do one little bit at a time. So that's a product, which separates as a sum. Well, now that's a product also. So I should be able to separate that as a sum as well. Natural log of 5 plus the natural log of y plus the natural log of x plus 1 squared minus the natural log of 2 minus 7x to the 1/3 power. Well, now those are as simple as they can get. You're not going to be able to simplify those. They're a single expression. They're a single expression in the argument. No products, no quotients, no powers. This one, well, I have a power there. And in fact, I have a power over here too. So let me pull out those powers. I can write this as the natural log of 5 plus the natural log of y. I'm just leaving those alone. That power 2 comes out as a multiple of the logarithm. It's going to be 2 times the natural log of x plus 1. It's a factor being multiplied times the logarithm. And now here I have a 1/3, which I can bring to the front. And I can write that as 1/3 natural log of 2 minus 7x. Once again, I'd love to separate this and this, but again, I don't have any properties that let me separate if I have a plus or a minus inside the argument. I can handle a plus or a minus on the outside of the argument. I can handle times, divide, or powers inside the argument, but I don't have anything that lets me handle pluses or minuses inside the argument. So that's about as far as we can go. That's as expanded as we're going to be able to get this. So this is our result. Incidentally, being able to expand an expression also has some computational value. Now, this has been made obsolete in recent years, in fact, in recent decades, because of the invention of, of these creatures here. Calculators have made a lot of computational things obsolete. We still use these properties algebraically, because of course these can handle numbers, algebra not quite so much. But let's take a look at a single example of something that has been made obsolete because of these things, but it does give us another illustration of what we mean by expansion, and it gives us, well, honestly, a little history lesson. It shows us where some of these things used to be used and how how life went on before we had the modern computer. So just a single example of this. It's still really just an example of expanding. So let's consider something like this. All right, so let's say we have some known value. Let's say I know that the log base b of the number 2 is 0.356. Let's say I know that the log base b of 3 is 0.565. And let's say I know that the log base b of 5 is 0.827. Now, these numbers are not easy to come by. It is possible to find the logarithms of numbers even without a calculator. The procedure can be kind of long and complicated. But the nice thing about logarithms is because of the properties that we've seen about condensing and expanding, you don't need to find every logarithm the hard way. Once you know just a few basic logarithms, which again can take a while to find, once you have just a few basic ones, you can use those to find a bunch of other ones that are a lot more complicated the shorter way. So here, log base b of 100. Well, I don't know log base b of 100. I only know these three. Right? It turns out that these three are enough to give us this logarithm. In fact, we don't even need all three of these. So let's say log base b of 100. Well, let me write that a different way. I'm going to write that as log base b of, 100 can be thought of as 10 squared. And say, yeah, but, well, so what? I don't know the logarithm of 100 or 10 squared or even 10. I don't know the logarithm of any of those. Oh, but look, 10 can be written as 2 times 5. Okay, fine. So what? So we can write this as log base b of 2 times 5 squared. Oh, but notice, I have a property that tells me if I have a power in my argument, I don't need to keep it there. I can bring it out. And instead of having to compute the log base b of this giant number, I can compute log base b of a much smaller number since the power is now on the outside. So that's now 2 times the log base b of 2 times 5. Okay, but I still don't know what the log base b of 2 times 5 is. Well, no, but this is a product. These are being multiplied together. And I know that 2 times log base b of a product can be written as 2 times log base b of the first number plus log base b of the second number. All right, that's one of our properties. If we have two things multiplied together in a logarithm, we can write them as the sum of the first factor plus we can write that as the sum of the log of the first factor and the log of the second factor. So if we have that property, that means that here these two numbers can be expressed as, well, these two separate arguments. But now I know what both of those are. I know log base b of 2 is that number. That's going to be 0.356. And I know log base b of 5 was that number. It's going to be 0.827. Oh, but those are just regular simple decimals. I can add them. Let's see here. Let's do this manually. We're not allowed a calculator in this class, and even if we were, the whole idea of this problem is to see what life was like before calculators. It was slow and tedious and slightly out of focus, according if you can tell from my camera here. All right, there we go. So we can add these together. So let's see, 6 and 7 make 13. 5 and 2 make 7, and 1 more makes 8. 8 and 3 make 11. You drop your decimal straight down. So that's going to be 2 times, the sum of these is 1.183. And if I double that, well, let's see, that's going to be 2.326. Oh, no, I'm sorry. It's going to be 2.366. And there we go. So even though I never computed this out on its own, the fact that I knew these three was sufficient to give me that result. So here, go ahead and give that a try. Go ahead and find the log base b of, oh, I don't know, let's say 15. All right, so pause the video, give it a try, and see what you get. All right, So log base b of 15, well, I don't know the log base b of 15, but I notice that I can write that as the product of 3 and 5. So I can write this as log base b of 3 times 5. But now, I have a property that says if I'm multiplying two things in an argument, I can simply write them as the sum of log base b of the first argument and log base b of the second argument. But those are both numbers that I know. Log base b of 3 is 0.565, and log base b of 5 is 0.827. And I can add those. So here that'll be 0.565 plus 0.827. So let's see here. 5 and 7 make 12. 6 and 2 make 8 plus 1 is 9. And 8 plus 5 gives us 13. Drop our decimal, and we end up with 1.392. So you see that even though logarithms can be hard to come by, once you know just a few basic ones, you can use them to find a bunch of others. As I said, this has been made obsolete in recent decades because of the advent of modern computers. Everyone carries one around with them in their pocket nowadays. But this is a nice view back into how this was used in previous years. But also it just gives you another example of how to expand. For the most part, we don't really worry about this anymore. What we care about are things like this, where we're doing algebra. Numbers, well, that's not quite as interesting anymore. Finally, the last thing, speaking of calculators, the very last thing we're going to be looking at in this section is one last property of logarithms. This is called the change of base theorem. Or sometimes the change of base formula. So it says let A and B be positive real numbers, not negative, not zero, be positive real numbers. Just like with every other logarithm, we're going to want our bases not to be 1, because again, that's not really a logarithm. Everything would just be the number 1. Let A and B be positive real numbers such that A is not equal to 1 and B is not equal to 1 either. Okay. For all real numbers, which we're going to call x. Actually, for all real numbers that are positive. So again, we don't want to deal with any negative arguments. For all real numbers that are positive, and we'll call those x, it's true that the log base b of x is equal to the log base a of x over the log base a of b. All right? So here, what this does is it allows you to change one logarithm of a particular base into something that involves a different base. The way it works is the log base b of x is, well, you can choose a new base. You can change it to log base a of x. But in order to do that, you're going to have to take your new logarithm and divide it by log base a of the original base. Now, this will work for any base, but the one we particularly care about is the natural base. So yes, this is true here, but the most commonly used version of this looks more like, so here note, the most common application of this is to change something from some other base to the natural log. The most common application is if you take log base b of x, that's equal to the natural log of x over the natural log of b. Here, you can change it to any base, but we often care about changing it to base e. Now you'll ask, well, just a second ago, you said something about calculators. I thought we were not allowed to use a calculator in this class. And we're not. But let's go ahead and bring something up about it anyway. Because, of course, math doesn't stop existing once we leave this classroom, once we leave this class. Math is used for all sorts of things. Chemistry, biology, physics, accounting, engineering, economics, and psychology. Right? Anywhere that numbers and things are, anywhere things are being quantified, you'll have numbers and you'll have algebra. Logarithms exist all over the place. Okay, so that must mean that I must have a calculator that lets me do this. After all, you said that this was obsolete now that calculators were a thing. Okay, so that must mean that if I want to find let's evaluate the log base 7 of 12. That must mean that I could just go to my calculator and just type that in. Well, you might if you have a very fancy calculator. Most calculators don't have that ability. Because if I look on my calculator here, I'm not very familiar with it. I don't use it too often. But I know for a fact, because I've checked, there is no log base 7 button on here. There's no log base 2 button either. In fact, there's only 2 logarithm buttons that I do have. I have the common log and I have the natural log. In fact, if you pull out your calculators, if you have one on your phone or something, take a minute. You can pause the video if you like and just check, see what logarithm buttons you have. I'd be willing to assure you that you almost certainly don't have anything besides these 2. In fact, a lot of calculators only have this one, the natural logarithm. So how would I compute this? Well, that's what the change of base formula is for, the change of base theorem. Again, there are other uses for it, but in this introductory class, we're not going to see many of them. This last example is more of a public service announcement. In case you need to use logarithms and exponentials in other classes besides math, you will almost certainly be allowed to use a calculator. And, well, here I'm showing you how to. If I have log base 7 of 12, I can't do that with this calculator. In fact, I can't do that with most calculators. But what I can do is I can change the base. Because if I have the logarithm of base b of x, I can change that to the natural log of the argument divided by the natural log of the original base. So the way that'll look here is I can write this as the natural log of the argument, which is the number 12, divided by the natural log of the base, which is 7. And those I can type into a calculator. Here I can take the natural log of 12, which is about 2.484906665. I say about because here my calculator runs out of space after this. This number actually does keep going, but that's as good as my calculator can do. You may have a much better calculator, but it will eventually cut you off somewhere. And this number goes on for a very, very long time. But that's a pretty good approximation. I can take the natural log of 7, all right, and that is approximately 1.945910149, approximately. And now, if I divide those two numbers, let's see, the natural log of 12 divided by the natural log of 7, and that gives me approximately, and again, here I say approximately because, again, these are not exact. My calculator cuts it off after a while, is approximately 1.276989408. Right? So, in application, this is extremely useful. In this class, we're not going to see the change of base formula much because, again, we're not allowed calculators, and nor is it something that we use algebraically at this level. But go ahead and give this a try. Go ahead and evaluate, I don't know, let's say log base. Here, let's make it as complicated looking as possible, and you'll still be able to do it just like that. Let's do log base 1/2. After all, a base can be any positive number except for 1. Let's take log base 1/2 of 3.8, because why not? So pause the video, give it a try, and then when you're ready, we'll go through it together. All right, everybody ready? All right, so we can write this as the natural log of the argument, 3.8, over the natural log of the base, which is a half. You can write 0.5 if you like. That's the same thing. All right, so now let's compute those. If I take 3.8 and I take the natural logarithm, that gives me approximately 1.335001067. And that's being divided by, well, let's see, if I take 1/2, my calculator actually lets me type in a fraction, 1/2. If not, you can use 0.5. The natural logarithm of that, and that's a negative 0.693144718. And if I divide those two numbers, if I take the natural logarithm of 3.8 and I divide it by the natural log of 0.5, that'll give me approximately, again, none of these answers are exactly correct, they're all approximations. Any answer you get with a calculator is an approximation. You're going to end up with negative 1.925999419. So if you ever needed a decimal approximation, you would write it that way. In an algebra class, usually we're okay with you leaving it this way. All right? But in an application setting, you might need a decimal approximation. So that's how you would get it. Same thing here in an algebra class. This is a perfectly acceptable number. That's a good way to write the answer. Just like I could write square root of 17. And I wouldn't need to find the square root of 17. That's just my answer. So that brings us to the end. So this completes our section, and I hope you all have a nice day.